When dealing with transformer secondary protection, specifically in relation to overcurrent protection device sizing, it's crucial to adhere to the National Electrical Code requirements. In this particular scenario, a 75 kV ampere transformer steps down 480 volts to 120/208 volts Y. The primary side is protected by a 100 amps overcurrent protection device. The initial question concerns the secondary protection using the 240.21 C6 exception, with 4/0 copper conductors running 25 feet and terminating in a 225 amps overcurrent protection device. The core issue is whether this 225 amps overcurrent protection device is appropriate or if it needs to be reduced. The correct answer indicates that the secondary overcurrent protection device needs to be reduced to 150 amps. Let's delve into the reasoning and calculations behind this. Firstly, consider the transformer secondary current. To calculate this, we use the formula apparent power equals voltage times current. Rearranging, we get current equals apparent power divided by voltage. For a three-phase system, this is further refined to current equals apparent power divided by the quantity of the square root of 3 times the voltage. In this case, the apparent power is 75 kV amperes, or 75,000 volt amps, and the secondary voltage is 208 volts. Therefore, the secondary current is calculated as 75,000 volt amps divided by the quantity of the square root of 3 times 208 volts, which is approximately 208.17 amps. Next, we evaluate the conductor ampacity. The provided scenario uses 4/0 copper conductors. Consulting NEC table 310.16, we find that 4/0 copper conductors with 75 degrees Celsius insulation typically have an ampacity of around 230 amps. However, NEC section 240.21 C6 addresses specific conditions for tap conductors, including those from transformers. This section has stipulations regarding the length of the tap conductors and the overcurrent protection device size. The key part of 240.21 C6 that we need to look at states when conductors are used for continuous loads, other than motor loads, the allowable ampacity of conductors shall be as given in table 310.16 for 75 degrees Celsius conductors, not 60 degrees Celsius conductors, multiplied by the appropriate factors from table 310.15. For conductors installed in raceways, the allowable ampacity shall be further adjusted by the factors of table 310.16 for ambient air temperatures and by the factors of table 310.17 for number of current carrying conductors. This means that we must consider both the continuous load and any applicable adjustment or correction factors for ambient temperature and the number of conductors in a raceway. A continuous load is defined as a load where the maximum current is expected to continue for 3 hours or more. In NEC section 210.19, A1 and 215.3, I require that branch circuits and feeder conductors be sized to carry not less than 125% of the continuous load. This is to account for the heat generated by the continuous operation. The overcurrent protection device must also be rated accordingly. Applying this to our 4/0 copper conductors, the ampacity is 230 amps. If this serves a continuous load, the maximum allowable current is 230 amps divided by 1.25, which equals 184 amps. This means that the conductors can safely handle 184 amps continuously. Furthermore, NEC section 240.4 B allows the use of the next higher standard overcurrent protection device rating if the conductor ampacity does not correspond to a standard size. However, this allowance is not unconditional. It's particularly limited by 240.21 C6, which governs tap conductors. Given the secondary current of approximately 208 amps and the adjusted conductor ampacity of 184 amps for continuous loads, the 225 amps overcurrent protection device exceeds the conductor's safe carrying capacity. The standard overcurrent protection device sizes near 184 amps are 150 amps, 175 amps, and 200 amps. Given the continuous load requirement, the 225 amps overcurrent protection device would not offer adequate protection. Therefore, it must be reduced. The answer suggests reducing it to 150 amps. This might seem low, but consider the NEC requirement that the overcurrent protection device should not exceed the conductor ampacity after adjustment for continuous load. Also, the tap rule in 240.21 C6 imposes constraints on the overcurrent protection device size relative to the tap conductor ampacity. In this scenario, the 25-foot tap length is also a factor. According to 240.21 C6, the tap conductors must have an ampacity of at least 1/3 of the rating of the overcurrent device protecting the primary feeder or branch circuit conductors. Here, the secondary conductor ampacity is 230 amps before adjustment for continuous load. Applying the continuous load adjustment, it becomes 184 amps. If we consider the tap rule, which states the ampacity of the tap conductors is not less than 1/3 the rating of the overcurrent device protecting the feeder or branch circuit conductors from which the tap originates, then the overcurrent protection device protecting the feeder or branch circuit conductors must be appropriately sized. In this context, a 150 amps overcurrent protection device would be a more appropriate choice, ensuring that the conductors are adequately protected from overcurrent conditions, especially under continuous load scenarios. The decision to use a 150 amps overcurrent protection device also considers the need to protect the transformer itself. Overcurrent protection is not just about protecting the conductors, it is also about preventing damage to the transformer due to sustained overloads. A smaller overcurrent protection device provides a quicker response to overload conditions, safeguarding the transformer's windings from overheating. To recap, firstly, calculate the transformer's secondary current. Secondly, determine the conductor ampacity from NEC Table 310.16. Thirdly, adjust the conductor ampacity for continuous loads by multiplying by 0.8 or dividing by 1.25. Fourthly, apply any necessary temperature correction or adjustment factors from NEC Tables 310.16 and 310.17. Fifthly, ensure compliance with NEC Section 240.21 C6 regarding tap conductor rules. Sixthly, select an overcurrent protection device that adequately protects the conductors and the transformer, considering continuous load requirements and tap conductor rules. Remember that the NEC is a comprehensive document, and electrical installations must comply with all applicable codes and standards to ensure safety and proper operation. In this specific instance, reducing the secondary overcurrent protection device to 150 amps aligns with these requirements, providing adequate protection for the conductors and the transformer. Also, bear in mind that local codes or amendments may impose additional requirements. Always consult the latest edition of the NEC and local regulations to ensure compliance. The selection of the overcurrent protection device rating requires a thorough understanding of the load characteristics, conductor ampacity, transformer capacity, and applicable code requirements. In this case, the 150 amps overcurrent protection device ensures that all these factors are adequately addressed, resulting in a safe and code-compliant electrical installation.